Central to the MultiCode RTx technology is the modified base pair ISO-C and ISO-G. The multicode base pair differs from the naturally occurring base pairs in the directionality of the hydrogen bonding pattern. As a result, ISO-G will only effectively base pair with ISO-C. This property enables the development of probe-free, real-time PCR systems that match the specificity and sensitivity of probe-based systems. During the denaturation phase of PCR, the strands separate. In the MultiCode RTx technology, one of the primers is unlabeled, and the other primer is labeled with a reporter dye. The labeled primer also contains a single multicode base ISO-C adjacent to the reporter dye. Unincorporated primers result in high initial fluorescence. As PCR reaction proceeds forward, the labeled primer is incorporated as part of the newly synthesized amplicon. The newly formed amplicons at the end of the previous cycle now serves as a template for the next round of amplification. Synthesis of the opposite strand terminates with the site-specific incorporation of an ISO-G attached covalently to a quencher molecule called dapsul. The resulting close proximity of the quencher to the reporter produces a decrease in fluorescence. The fluorescence decrease is directly proportional to the amount of amplicon formed. The raw fluorescence data is captured by the instrument and graphed by the MultiCode RTx analysis software. The y-axis represents the relative fluorescence units. The x-axis shows the number of PCR cycles performed. From this graph, we determine the cycle threshold, commonly referred to as CT, or crossing point CP. CT is the PCR cycle number at which a decrease in fluorescence signal is detected. CT values are lower when a specimen has a higher initial target copy number and vice versa. CT values can therefore be used to quantitate the amount of target present in a specimen. The flat part of the curve represents the high initial fluorescence resulting from unincorporated primers at the start of PCR. As the reaction proceeds, the decrease in fluorescence due to the site-specific incorporation of ISO-G associated quencher is shown as the downward curve on the graph. Following completion of amplification, a thermal melt is performed. The reaction is heated. Heating causes the DNA strands to separate. As the strands separate, the quenching effect of the reporter is reduced, resulting in increased reporter fluorescence. Data collected by the instrument is graphed on the MultiCode RTx analysis software as a melt curve. The x-axis here shows the temperature range. The y-axis shows the rate of change in fluorescence over this temperature range. The peak of the curve represents the maximum rate of change in fluorescence and is defined as the Tm of the target. Tm is a function of amplicon length, base composition, and reaction conditions. Differences observed in the Tm of analyzed targets can be useful to confirm the identity of amplification products and to differentiate them. In summary, MultiCode RTx is a probe-free, real-time PCR technology utilizing the synthetic base pair ISO-C and ISO-G. This technology employs CT and melt curve, or TM analysis, to detect, quantify, and differentiate analytes. To learn more about MultiCode products and technology, please visit the Luminex homepage at www.luminexcorp.com. We thank you for your interest in Luminex and our MultiCode technology.